Welcome to the Gresty Academy 25 must-know college entrance exam questions on limits and continuity. Okay, so let's get straight stuck in. The first 8 questions are on this graph here, very common type of question. So question number 1, we want to know the limit as x approaches minus infinity of f of x. All we do is we follow this blue line here as x approaches minus infinity here. Clearly f of x is approaching 0 and therefore the limit of question 1 is 0. Nice easy start. Question number 2, the limit of f of x as x approaches minus 2 from the negative side, i.e. from the left. Okay, well for that what we need to do is follow the blue line, but now we follow the blue line this way. We're following it towards minus 2 but from the left here, and clearly that limit goes right down forever. There's going to be an asymptote here and its limit is minus infinity. Okay, now the limit, question 3, limit as x approaches minus 2 from the plus side. Well, this time we're approaching minus 2 from this side, so we go along the green line. So we will basically be going along here as we approach minus 2 from the plus side, and that one is actually going to go up to plus infinity. So the answer to question 3 is plus infinity. Let's have a look at question 4. Question 4 is saying the limit as x approaches minus 2. Okay, right, well, because the limit from the left is minus infinity and the limit from the right is plus infinity, they're not the same, and therefore the limit as x approaches minus 2 does not exist. Okay, question number 5. Now we're looking at the limit as x approaches 1 from the negative side, i.e. we're going along the green one here from the negative side. Don't worry about this open circle here. It's the limit that we're interested in, i.e. what does it approach as we approach 1? Well, as we approach 1, it approaches 2. So the limit as x approaches 1 from the negative side is 2. What about the limit as x approaches 1 from the right? Well, this time we're going to follow this orange line here. As we approach 1 from the right, it is going to approach 4. So the limit as x approaches 1 from the right is 4. Let's have a look at the 7th question and the 8th question. Question number 7 is now saying, okay, what's the limit as x approaches 1? Well, as when x approaches 1 from the left and when x approaches 1 from the right are different, therefore the limit as x approaches 1 does not exist because they must approach the same number. And there's a very good example in question 8. Okay, the limit as x approaches 3. Here's 3 here. Now we can see that there is an open circle here, meaning that the function at 3 is actually this purple number here. So f of 3 is actually equal to 2, not that the question asks us that. So basically, let's have a look. The limit as we approach 3 from the left is 1. The limit as we approach 3 from the right is also 1. As the limit is the same approaching from the left or the right, therefore the limit exists and the limit is 1. The fact that there is a discontinuity at the point 3 is irrelevant. F of 3 exists and it equals 2. The limit as we approach 3 of f of x equals 1. What is the problem here is that it's not continuous or differentiable at 3. Okay, so that's question number 1 to 8. They're very common there. Let's have a look at question number 9. Okay, question number 9, all we need to do, we want the limit as x approaches minus 2. This one's a relatively straightforward one. We just plug in minus 2. So that will be 3 times minus 2 squared minus 5 times minus 2, add 1, and that basically equals 23. So the limit as x approaches minus 2 of that is 23. So that's the answer to that one. Question number 10. Okay, if we plug in 4, the problem here, if we plug in 4 on the top and the bottom, we get 0 over 0, which is no help to anyone. So we need to factorise this quadratic. We need to factorise as x minus 4, x minus 2 over x minus 4, x minus 1, and then we can cancel out those x minus 4, leaving us x minus 2 over x minus 1. And then when we stick 4 into that, we get 4 minus 2 over 4 minus 1, which equals 2 over 3. So the limit is 2/3 for question number 10. Okay, what about question number 11? If we plug x equals 5 into this, we again get 0 over 0. So we need to rewrite this and factorise. We need to rewrite it as x minus 5. Well, this by difference of two squares factorises as x minus 5, x plus 5. And we can cancel out the x minus 5. And that leaves us with 1 over x plus 5. And then when we put 5 in there, that gives us 1 over 5 plus 5, which is 1/10. So that limit of this one, question 11, is 1/10. Let's have a look at question number 12. Okay, question number 12. It's a little bit more difficult to see the factorisation here, but in actual fact, by difference of two squares, we can rewrite this as root x minus root 8 over root x minus root 8, root x plus root 8. And the root x minus root 8 cancels out. Oh, sorry, I forgot to say, if we put 8 in here, we would again get 0 over 0. That's why we need to factorise. And so basically that gives us 1 over root x, add root 8. And now we can stick 8 in, which gives us 1 over 2 root 8. And we can simplify that to root 2 over 8. And that is the limit for question number 12. Okay, we're doing well here. Question number 13. Okay, now basically question number 13, the degree of the top is 2 because the biggest power of x is 2, and the degree of the bottom is 2 because the biggest power of x is 2. So as x approaches infinity, all of the other stuff will basically become irrelevant, and the only important thing will become the coefficient of the numerator and the coefficient of the denominator of the highest power, which is x squared. And so therefore this limit as x approaches infinity will be 5 over 3. It would also be the same limit as x approaches minus infinity, by the way, because that would be x squared and x squared. Okay, question number 14. Okay, when we get again, we can look at the degree of the numerator and the degree of the denominator. As the degree of the numerator is 1, i.e. x, and the degree of the denominator is 2 because it's x squared, this one is going to far dominate this one as we approach infinity or minus infinity. And so clearly this one, the limit is going to equal 0 because the denominator is going to be so large as we approach infinity. Okay, question number 15. Right, let's have a look. Okay, now what we're doing is classifying discontinuities. So let's have a look at this one. If we factorise this one, we get x minus 2, x minus 3 over x minus 2. And, no we don't, x minus 2, x plus 3 over x minus 2. And basically what that means is that for every part of this f of x, except for x equals 2, it's perfectly continuous. At x equals 2, we have a removable discontinuity, i.e. the answer is this one here. And the reason why it's called a removable discontinuity is because if we defined here f of 2 to, for example, equal 5, then everything would work because we've defined what f of 2 is and we now have a continuous function. So that's why it's called removable, because we can remove it by defining f of 2. Okay, question number 16. Let's have a look at this one. Now this one's different. We can't get rid of this discontinuity, but when we put x equals 1 in here, this becomes 0, and whenever the denominator becomes 0, it goes up to infinity. So this will be an infinite discontinuity at x equals 1. Okay, question number 17. Let's have a look at this one. Now basically, as x approaches 0, this oscillates wildly, and cos oscillates between +1 and -1. And so basically, as we get x approaching 0, so if we have a graph here where x is 0, it goes wilder and wilder and wilder like that between 1 and -1, never settling on anything. And in fact, the closer x gets to 0, the more wildly it oscillates. So this is an oscillating discontinuity at x equals 0. Question 18. Okay, now this one, this is a piecewise function. This is the function when it's less than 3, and this is the function when it's greater than or equal to 3. So what we need to do is we need to plug 3 in here. So basically, as x approaches 3 from the minus side, we look at this one. So that means g of x will be equal to 2 times 3, add 1, which is 7. As x approaches 3 from the plus side, we use this one because this is where x is greater than or equal to 3. So g of x is equal to 3 squared minus 5, which equals 4. So we can see that x approaches 3 from the minus, it's 7. As x approaches 3 from the plus, it's 4. They're not the same limit, and therefore we have here a jump discontinuity, because at 3 it suddenly jumps from 4 up to 7. So it's jump discontinuity, x equals 3. And finally, this one, question number 19. Question number 19, the denominator here never hits 0, because x squared is always greater than or equal to 0 for any number. So x squared plus 1 is obviously always, x squared plus 1 is always greater than 0. So the bottom is fine. At x equals 3, the top is 0, but that's fine. We just basically have that f of x equals 0. That's perfectly valid, though, nothing wrong with that. So in actual fact, this one, there is no discontinuity at all. It is continuous everywhere. Okay, question number 20. All right, now, so basically, again, we have to look at the limit as x approaches 3 from the negative side. Well, as this part of the piecewise function is where x is less than 3, we look at this part of the definition, and basically we would say that basically f of x approaches 3 from the negative side when x squared plus 1, we put 3 in, so that would be 3 squared add 1, which equals 10, and therefore the limit of f of x as x approaches 3 from the negative side is equal to 10. Question 21 is an interesting one. Okay, so basically we need the limit. In order to make this piecewise function continuous at x equals 2, the limit as we approach 2 from the minus must equal the limit as we approach 2 from the plus. So we stick 2 in here. This will be the limit as we approach 2 from the minus. So 2k add 5 must equal the limit as we approach from the positive side, 2 squared minus k. And solving this will give us 3k equals minus 1, i.e. k equals minus a third. And that ensures that the piecewise function is continuous at x equals 2. Okay, question number 22. Let's have a look at this one. Question 22. All right. So basically, we need to select one of these expressions here in order that this piecewise function is continuous everywhere. Okay, well, basically we have 3 points where we have to be, well, 2 points where we have to be really careful. First of all, 0. We need, as x approaches 0 from the minus, to be equal to x approaching 0 from the plus. So let's have a look at that. X approaching 0 from the minus side, we use this. So that would be 2 times 0 add 3. So basically, g of 0, putting 0 in from the plus side here, g of 0, which is x approaching 0 from the plus side, must equal x approaching 0 from the minus side, which we've just established is equal to 3. And then we have to look at 1 as well. So x approaching 1 from the plus side will be this function here, which will be 1 squared add 1, which is 2. And x approaching 1 from the minus side will be our function g of x. So we need g of 1 to equal 2 as well in order for it all to be continuous. Now, if we look at these 5 value g's here, the only one that has g of 0 is 3 and g of 1 is 2 is b, g of x equals minus x plus 3. Okay, question number 23. This is on the intermediate value theorem. Okay, so basically as the function is continuous, and at f of 0 it's minus 2 and f of 5 it's 8, and it's continuous on that interval, therefore it must, by the intermediate value theorem, it must cross the x-axis. We draw a nice little graph. So we have here 0 and we have 5. So f of 0 is down here, minus 2, and f of 5 is 8. If it's continuous, it must cross the x-axis at least once. It doesn't have to cross only once. It could, for example, go like that. So basically the intermediate value theorem doesn't say it crosses once, it says it must cross at least once. And so therefore the answer for this is C. There is at least one route, i.e. where it crosses the x-axis. At least, not only. Okay, question number 24. A function is continuous on this closed interval, and we're given that basically, let's just draw this out. So basically we have f of 0 is minus 3. That's minus 3 here. F of 1 is minus 1, so that will be about that point there. F of 2 is 4, so that will be about that point there. And f of 3 is 2, so that will be about that point there. The intermediate value theorem guarantees a root must exist on which interval? Okay, well, basically, here and here are on opposite sides of the x-axis, so therefore at least one root, if it's continuous, must be between 1 and 2, and therefore the answer is this one, 1 and 2, B. There doesn't have to be a root here because they're both negative, but there could be. We don't know whether there is or there isn't. It could go like that, for example. We don't know. And it could go like that. So we don't know. All we do know is there is definitely a root, at least one root, on the interval 1, 2. Okay, finally, question number 25. This is the final one. So it's continuous on the interval 1, 4. Okay, well, let's draw 1. Let's draw 4. F of 1 is 1. And f of 4 is 6, somewhere up here. The intermediate value theorem tells us, okay, which one of these 5? There's no solution to fx equals 2, so it's looking at fx equals 2, which is this line here. That's f of x equals 2. Well, clearly, if f of 1 is 1 and f of 4 is 6, it has to cross this line somewhere, so it certainly isn't that one. There's exactly one solution to fx equals 2 on the interval 1, 4. Well, I mean, it could do that. So that's not true as well. The answer is there is at least one solution to fx equals 2 on the interval because it must cross from this side of fx equals 2 to that side. We don't know how many times it's going to cross, but it must cross at least once. So the answer is this one here. Just going through on the other ones, there's at most one solution. Well, we just established that it's not necessarily true. There's at least one solution to fx equals 0 on the interval 1, 4. Well, that one's an interesting one because fx equals 0 is the x-axis. We don't know that it actually crosses the x-axis. It may do, but we don't know that it does, so that one's wrong. And there's no solution to fx equals 0. Well, again, we don't know. It could do what I just did there, and maybe it doesn't. So it's not that one, so the answer is this one. Okay, well, there are 25 must-know college entrance exam questions on limits and continuity. I hope you've enjoyed this, and I hope you found it useful. If you have, please like this video and subscribe to the Gresty Academy YouTube channel. Okay, thank you very much.